Welcome to Measurement Study of a Process, Lesson 2. In Lesson 1, we looked at a hypothetical scenario involving the manufacture of 50 bored out parts, of which 2 parts were found to be outside of the tolerance for the bore. We performed a measurement study, constructed a tally chart, a histogram, then determined a bell curve over the histogram. We learned that no manufacturing process can produce identical parts, and that differences in parts is known as variation. We were asked how we could ensure that all parts would be bored out within tolerance. Let's look at a process. A process, put simply, is a series of elements made to an input to produce an output. For the boring process, the process requires each of the elements shown above to produce a bored out tube. Variations in a process. For the boring process, each of the process elements could have causes of variation. And here we can see the elements that we saw in the process and common causes of variation. So with people, there's a choice of setup, fatigue, experience. For the machine, its speed, operating temperature, feed rate, wear rate. For material, its composition and its dimensions. The management, for lubrication, operation and instructions for the process. The method, dimensional accuracy, calibration, and environment, humidity, temperature and vibration. Stability. Common causes are the many sources of variation that are always present. A process operates within normal variation when each element varies in a random manner within expected limits, such that the variation cannot be blamed on one element. When a process is operating with common causes of variation, it is said to be stable. Process control. The process can only be termed under control if it gives predictable results. Its variability is stable over a long period of time. Graphs and charts have to be chosen for their simplicity, usefulness and visibility. They are simple and effective tools based on process stability monitoring. They give evidence of whether a process is operating in a state of control and signal the presence of any variation. In Lesson 1, we constructed a histogram and produced a bell curve based on the measurement of 50 parts. We found that 2 of the parts were outside of the tolerance. However, those parts were all measured in random order after the boring process had been completed. To determine if a process is under control, parts need to be measured during the process. Before this, we need to understand a little about statistics. We will now look at different statistics, what they mean, and how we can use them to improve our processes. Both of these symbols are Greek letters called sigma. We will see more of them later. Range is equal to the spread of the extreme results. So for this example, find the range of 4, 6, 7, 9, 4, 2, 5, 8, 7, 9 and 3. The extreme values, those values at either end of all the results, are 2 and 9. The range we can call R is equal to 9 minus 2 equals 7. So the range is 7. Mean is equal to the arithmetic average, which we call x bar, and is written as an x with a line above it, and that's equal to sigma x divided by n, where sigma is equal to the sum of x's and n is equal to the sample size. Find the mean value of 4, 6, 7, 9 and 4. We know the formula x bar equals the sigma of x over n, which is equal to 4 plus 6 plus 7 plus 9 plus 4 divided by 5. This is equal to 30 divided by 5, which equals 6. So the mean value is 6. The median is equal to the middle value. Half of the values are greater than the median and half are less than the median when the values are placed in numerical order. Find the median value of 4, 6, 7, 9 and 4. First, put the numbers in numerical order. Now we have 4, 4, 6, 7 and 9. The middle number is the median, and there we can see the median is 6. So the median number is 6. The mode is the most frequently occurring value. Find the mode value of 4, 6, 7, 9 and 4. The most popular, as it appears twice, is 4. So the mode is 4. For a perfect normal distribution curve, the mean, median and mode all have the same values and lie at the same point. Our frequency chart from lesson 1 tells us the mode, as 2 appears twice, equals 2. The median, if we arrange all of the totals in order, is equal to 6. And the mean, if we add all the values up and divide them by 7 values, equals 7.14. So we know the mode, median and mean. However, as we saw earlier, for a perfect normal distribution curve, the mean, median and mode all lie at the same point. Our values are not all equal, so we do not have a perfect distribution. Discuss in your class why the distribution is not perfect. For the bore diameter data, we plotted the data and made a bell curve, so we had normal distribution. But was all data within tolerance, and is it skewed? Let's look at the bore diameter data and the tally chart. The data that we saw for the bore diameter showed that 2 parts were out of tolerance, so this might have an effect on the location of our bell curve. But our data is also skewered, i.e. there is a greater total, 12 plus 5 plus 2, below the centre point, 16, than there is above, 7 plus 6 plus 2. Let's look at the distribution curves and their location. Line XX is the location of curve A. Line YY is the location of curve B. Both curves show a normal distribution, except that the data for curve B is spread towards the top tolerance. Let's look at the shape of distribution curves. A is a normal distribution curve. B is a skewed distribution curve. Curve B is an exaggerated representation of our data curve. Let's look at the bore diameter data again. The requirement is 36.32 plus or minus 0.05 millimeters. So the bell curve has a shifted location to between nominal 36.32 millimeters and top tolerance 36.37 millimeters. We can also see that there is more data below the center point than there is above it, so the distribution is skewed. In the next lesson, we will look at how statistics can be used to tell us how well a process is under control and how to develop a process control chart. All lessons will lead us to understand how not to make parts out of tolerance.